Hello, everyone. Let's continue the discussion that we had before. So we have now interpreted the estimated value of DI. How do we interpret now the coefficients of a linear probability model? Here, what you need to keep in mind is basically that the coefficient of a linear probability model would indicate the change in the probability that DI is equal to 1, which is caused by a unit increase in the independent variable in question. See, before, in our normal regressions that we have seen. For example, if beta 1 hat is equal to, let's say, zero point 0.5, what would that mean? That would mean that for every unit increase in this independent variable, right, it increases the dependent variable by a value of 0.5, isn't it? That is basically the way in which keeping Ri constant. That is basically the way in which we interpreted normal regression model, right? In this linear probability models, right, what the coefficient values, that is beta 1, beta 2 hat, beta 1 hat or beta 2 hat, what it would indicate would be the change in the probability that di is equal to 1, which is caused by a unit increase in the independent variable in question. Okay, for example, if fi is increasing by, let's say, 1%, okay, because it is the percentage of females within the state's population. If it is increasing by 1%, right, what change would happen to the probability of DI, right? That's basically what is captured by this coefficient beta 1 hat. Okay, so it goes without saying that the other independent variable is held constant. Okay, so we have seen how to interpret the value of DI hat, right? And also how to interpret the value of the coefficients, right? However, linear probability models have their own problems, right? First and foremost problem that it faces is R squared, adjusted R squared value, which is basically a measure of overall fit of the model, right? The overall fit of the model is basically what we measure through adjusted R squared, right? In our earlier discussions, I have told that R squared is not reliable at all positions, at all in all cases. So that is why we go for adjusted R squared. When it comes to linear probability models, this adjusted R square is also not very reliable. Essentially, because of this nature in the which we do, nature of the dummy variable, because dummy variable takes only binary values, no, 1 and 0. So because of which it has certain inherent problems, because of which the R squared value becomes kind of unreliable. It is R squared, huh? I'm sorry. Right. Because of which the R squared value becomes unreliable. So as a result of which, we have other mechanisms through which we try to uh, find a solution to this problem, to the unreliability of R squared. Unreliability of R squared is essentially because of this binary nature of this dummy variable, which takes only values 1 and 0. Okay, so that's one of the problems that the linear probability model faces. Now, the second problem is basically that di hat is not bounded by 0 and what is the necessity that, or why do we expect it to be bound within 0 and 1? See, what is di hat? Di hat, as I have mentioned here, is the estimate of the probability that di will be equal to 1. It's a probability, right? Huh? Di hat is a probability value. So it's quite natural, as people who have studied probability, it's quite natural for us to expect the fact that the value of di hat might be confined within 0 and 1, isn't it? Because having a value greater than 1 doesn't make much sense, isn't it? And if you are also talking about value being equal to 1, then it means that the event is going to happen with in all certainty. There is 100% chance, which is kind of very, very rare or very unlikely and very unreasonable to have such kind of a estimate, isn't it? Here the problem is not just that it is it would be, it is not within 0 and 1. Sometimes it might be somewhere beyond this. Okay, for example, you consider this equation itself that I have written down here. That is beta 0 hat plus beta 1 hat fi plus beta 2 hat ri. Let's say that the estimated values of all of these components are equal to 1 each. Okay, just a very hypothetical case. Okay, so then what would it mean? It would mean that it is 1 plus 1 plus 1, which is equal to 3, which means that di hat now has a value equal to 3, isn't it? Why does this happen? This is again a problem with the binary nature of the dummy variable. So it is this problem is basically what is called as the problem of unboundedness. Okay, the di values are unbounded. Okay, these di values are unbounded in one sense. So that is essentially one of the reasons as to why the this problem crops up. Right now, that being the second problem, the third problem is basically that the error term. The error term is neither homoscedastic, right, nor normally distributed, which means that there is the problem of heteroscedasticity and non-normality that is found with regard to the distribution of the error terms. Okay, this is a major problem that you will come across, especially in the case of uh, linear probability models. Right, there is heteroscedasticity and non-normality in the case of the distribution of the error term. However, this is not a very serious problem. Therefore, in many cases, researchers usually ignore this problem that is often seen. However, these are three major, we can say, limitations that we face with regard to linear probability models, which is the reason why we always resort to other types of models. For example, in the earlier, one of the earlier recordings, I have talked about uh, a model called as a binomial logit model, right? Binomial logit model tries to cover some of these difficulties that are associated with the linear probability model. Okay. Now to go ahead and talk about a little more on the problems related to linear probability. I have told you that adjusted R square becomes unreliable. So what do we do? As a coping mechanism, you have a new statistic that is often used in the case of linear probability model, which is called as pseudo R square, right? This is usually represented as R square P. Okay, right? Usually when we see the regression results of linear regression model, linear probability model, you will also, along with adjusted R square, you will also see another measure called written there, which is R squared P, which is nothing but the pseudo R square, right? We are not going to get into the technicalities of this because that would entail a deeper discussion as such. As of now, understand this, that pseudo R squared is simply the average of the percentage of ones that are explained correctly and the percentage of zeros that are explained correctly. Okay, see, dummy variables take a value 0 or 1. Okay. In the list of observations or estimates that you get, observed DIs, in the list of observed DIs that you get, you look for out of, let's say, 100, right? How many ones are there and how many zeros are there, right? Percentage of ones that are explained correctly and zeros that are explained correctly. And you take the average of the both, average of both. Okay. That's basically the measure of pseudo R square, right? It is considered as a comparatively better measure and a more reliable measure when it comes to linear probability models, as R squared is kind of unreliable. And to deal with the problem of unboundedness, which I have just explained, right? What do you do? One method that is usually done is you assign the value of 1 for all DI hats whose value is above 1. If your DI hat is above 1, as I have just mentioned before, if your DI hat is equal to 3, right? Since it is a value above 1, you just assign the value of 1 itself. Okay. Uh, for all values which are above 1. And for all negative values, you assign the value 0. However, this is again a problematic thing, because here, even if you assign di hat equal to 1, what would that mean? It would mean that there is 100% chance, which is very unlikely. So the problem of unboundedness, if you are trying to deal it this way, you are trying to kind of what do you say, ignore the problem rather than address the problem in a constructive manner. The problem of unboundedness is kind of addressed in a meaningful way in what we called as the binomial logit model. Okay, so these are essentially the this is essentially the sum and substance of what we call as a linear probability model. Now we will see an example in the upcoming recording. Okay, that will complete our discussion related to linear probability. Thank you.